Okay, guys. So we've seen all this cool new behavioral economic stuff, and um, it's made its way into the mainstream by using data. And that seems like a really good idea, right? Like, rather than starting with theories about how you think people should act, why didn't we always just start with data about how people really do act? We've seen that theory can seem kind of plausible, but sometimes it makes predictions that actually don't seem to pan out. Okay, so we've seen all these behavioral quirks and stuff. But unfortunately, the alternative of just starting with data, it's not foolproof either. There are problems, and this unit is going to talk about a specific problem that's occurred in behavioral economics, but also many other fields that rely on basically statistical driven science. It's called the replication crisis. So, what's the replication crisis? Basically, as I've said here, we're going to use data in behavioral economics to try to argue for our point. But the replication crisis is basically the phenomenon that over the last five years or more, a large number of influential empirical, that means data-driven results, have failed to be replicated by later scientists. Okay? So let's look at some actual numbers. What is a replication? A replication is an attempt to independently verify somebody else's finding. It could be that you take the same data that they had, they lend it to you, and you reanalyze it. Okay? It could be as simple as you actually rerun the code that they did to just make sure that they didn't make a typo in writing down the results. It could be that you get the same data, but you decide how you're going to analyze it yourself. Or it could be that you collect new data about the same effect. So a paper by Colin Kammerer and many others in 2018 found that 11 of 18 economic experiments, so that's the kind of stuff that we've been looking at, successfully replicated. But typically when they did replicate, and notice this is only 11 out of 18 times, the size of the effect was much smaller than initially found. Another paper, Chang and Lee from 2015, they had basically the simplest possible, easiest replication. They tried to they wanted researchers to basically send them the code and the data from various studies, and they were just going to rerun it. And they could only do that in about a third of the cases. The code had been lost, or the respondents wouldn't share it. In any ways, 2/3 of the data couldn't be independently verified, or 2/3 of the results. Most famously, a paper by Arts and many others found they did a huge study of psychology experiments, 100 different psychology experiments, and depending on how you define a successful replication, only 1/3 to 1/5 of them were successfully replicated. Okay. And so this is now something that mainstream news has picked up, although these articles are now a couple of years old. So people are aware of this. So what does it exactly mean to fail to replicate? So this is, by the way, a short primer on hypothesis testing. So this is the kind of thing you would normally learn in a statistics class, but I can't tell you. I think it's important to learn about behavioral economics in an Econ 301 class, but I also think it's important to learn where this behavioral economics results comes from and to be aware of challenges in these results. So that's why we're going to cover this second half of the behavioral econ unit. So, a short primer on hypothesis testing, which is how you do this empirical data stuff. If you want to go back to the philosophy of science, there's a famous philosopher named Karl Popper, and he's really influential among scientists. And his big idea was that you can never really prove most theories, okay? But you can, because they're an explanation, and you never can prove beyond all doubt that explanation is the right one. You can, however, disprove theories because they make predictions, and if they make a prediction that's right, well, that's good, but of course multiple theories might have made the same prediction, so that doesn't prove it's true. But if they make a prediction and the prediction is disproved, is wrong, well, then that shows that your theory's not right. So we can't ever prove a theory, but a theory that's been tested a lot, that makes a lot of predictions, and they're all right, is probably in pretty good shape. So let's suppose that a theory predicts a certain specific set of observations. We can go look at the data and see if those observations are present. But what if our theory's wrong, and actually it was just blind luck that those observations happened to appear in a way that seemed to support the theory? Okay? The solution to this that economists, statisticians, and basically all natural scientists or experimental scientists, everybody uses this, is to calculate the probability, which is called the p-value, that these observations would have occurred simply by chance. And we call this the null hypothesis. So the null hypothesis is basically that these things would have occurred typically by we assume some kind of probability that this would occur by chance, and then we calculate what's the probability these actual data occurs under that null hypothesis. If the probability that chance alone could generate these results is sufficiently small, so in economics that's typically around 5%, so if there's less than a 5% chance that the data looks this way just by random chance, then we reject the null hypothesis as being very unlikely, and that makes us more confident in our theory. Okay, so this is, I think, most clearly explained with an example of something we've studied. So remember we talked about the trading game to try to find the endowment effect and prove that it exists. And the way that Richard Thaler and others did this, I think it was Thaler, it might have been Kahneman, they had 44 participants. We randomly allocate them all coffee mugs that say Cornell on them. And under the standard economics model, we would expect everybody whose value of the mug falls below the median. So right now we've arranged everybody from the person who has the most value from a coffee mug to the person with the least value. And everybody down here is in the bottom half of the valuation of coffee mugs, and so it should be possible for those who more value them to offer a mutually beneficial trade, like I'll buy your coffee mug and you'll get more money than the coffee mug is worth to you, and I'll get the coffee mug which is worth more than the money is worth to me. So if that's right, we would expect to see everything look like this at the end, but what they actually found when they did the experiment is it looked sort of like this. So there were fewer trades than expected. Okay. How do they know, though, that the number of trades was sufficiently less than expected? So remember, their hypothesis is that people's valuation of a mug depends on ownership. But there could also be a null hypothesis that generates this same data. A null hypothesis is, let's assume, people's valuation is actually independent of ownership. We had 44 participants. We distributed among them 22 coffee mugs. And if we see fewer than 11 trades, that's evidence of this endowment effect. However, it could be that the endowment effect is false, that the null hypothesis is true. Remember, the null hypothesis is basically that people's valuation is independent of ownership, but we just happened to, by chance, give more than 11 of the mugs to people with a higher than median valuation. Okay? So this is how we distributed the mugs. By chance, we would expect half the mugs we give out to fall to people in the bottom half of the distribution and half to fall. But that's only going to happen on average. We could get unlucky and happen to give, instead of 11 out of 22 mugs to people in the top half, what if we gave 16 out of 22 mugs to people in the top half? Well, those 16 mugs wouldn't be traded, and we would observe less than 11 trades, and we would falsely conclude it's evidence for the endowment effect. Fortunately, we can precisely calculate the probability that that happens. What is the probability that some number x out of 22 mugs go above the median? This is the kind of calculation that we don't really have to do in this class, but I want you to understand the logic of where these experimental results interpretations come from. So we can actually calculate that to yield a p-value. If you care, I'm going to use something called the binomial distribution to calculate the probability that X events occur out of N trials. You don't need to know that for this class, though. So we can just do this online, and the probability that more than 11 of the mugs go to people in the top half out of 22 distributed mugs is actually pretty high. 42% of the time, you're going to have at least 12 mugs, maybe more, go to people whose valuation is above the median. Okay? But as we increase that X, the chances get smaller and smaller. The probability that more than 14 people in the top half get their mugs is only 7%. So only 7% of the time, if we did this experiment a lot, would we find 15 or more of those 22 mugs accidentally distributed to people whose valuation is in the top half. And remember, they only observed 2.25 trades on average, which for that to occur, if we're distributing 22 mugs, we need about 20 of the mugs to be distributed to people in the top half of the distribution. The probability that that would happen purely by chance is really small, not a lot less than 5%. It's actually only 0.01%. And so that is why this result is compelling, basically, because we expect 11 trades under the null hypothesis. There's some probability we'll get less than 11 trades just by chance, because we might get the mugs not actually distributed how we want. But the probability that we would only see 2 trades if the null hypothesis is true is really small. And so we consider that disproven, basically. There we go. It is extremely unlikely that the null hypothesis would generate the observed data. Okay. However, that's how it's supposed to work, and yet we have this replication crisis. So what is the problem? Well, there's several reasons a study's results might be unreliable. In the next videos, we'll talk about 3, and also how scientists have adapted and recognized these problems and tried to correct them going forward.